Welcome to our video report on Practice 4, Conductivity of Composite Materials. We are group number 2 from Section 2. In this video, we'll start with an introduction, then we'll present the methodology, the results, then we'll analyze and discuss these results. We'll conclude, and finally, we'll present the references. The main objective of this practice was to design a protocol to determine the difference in thermal conductivity between composite and pure materials. For the introduction, we will start by defining what is thermal conductivity. First, we need to know that heat transfer mechanisms are conduction, convection, and radiation. For this practice, we'll only focus on conduction. So, what is thermal conductivity? It's a property of materials that indicates the capacity of said material to transfer energy as heat. This property is important when we are designing a process or a product because we need to know if we have to make the flow of energy high or low. The units are watts over meters times Kelvin, and this property depends on temperature, material properties, and composite materials, which is the main focus of this practice. Moving on, we need to know how this transfer of energy as heat happens. So in order for heat to be transferred, there has to be a temperature difference between the surfaces. For the materials, the electrons and phonons are in charge of this transfer. Depending on the type of material, one dominates over the other. For example, like in metals, electrons are the ones that dominate for this transfer of energy. As for other types of material, like non-metals, the phonons dominate the transfer of energy. Fourier's law is a mathematical expression that describes what happens in the transfer of heat. Here we have three different variations of this law. The top left applies only when the delta temperature is very small. The top right, it's the vector of flow of energy. It's the multiplication of the conductivity times the gradient of the temperature. And the bottom equation applies for when the system has a constant pressure. This is the equation that we will use for this practice.
Now I'm going to explain you the methodology that we use in the practice. But here we have two different methodologies that we use. The first one is the methodology proposed by the group, and the other one is the methodology that we actually use in the practice. Here is the methodology proposed by the group. This is a sketch and the actual setup of the methodology that we proposed as a group. This is the assembly of the process methodology that we proposed. First, we have a tank with internal dimensions of 24 centimeters by 25 centimeters and a height of approximately 20 centimeters that contain between 5 and 7 liters of water with crushed ice. Then a polystyrene box was used as a container for hot water. We use glasses made for different materials that we are going to measure the conductivity, and each cup was filled with hot water. The cup prepared in the way was measured in the tank, and the temperature of the water in the cup was measured with the thermometer for a few minutes. And finally, the temperature of the ice water mixture in the tank was also monitored and highly shaken once a minute to avoid local temperatures increases close to the cup temperature. How thermal conductivity is measured with the methodology proposed by the group. To measure the thermal conductivity of different materials, the cooling water temperature was measured as a function of the time in 5 different glasses made of different materials. The temperature was measured with the external thermometer with a system. Then the thermal conductivity is calculated from the slope uh, fitted to the time versus radio. And the equation that we use is this one of the radio. Here is the methodology used in the practice. First, we have to cut the strands to a length of 9 centimeters. Then we have to define the delta for the distance for all the filaments and mark the distance between them in the filament. Then we have to preheat the iron to 120 Celsius, and then we have to glue the filaments to the iron. Then we have to define the delta of the time and how often we are going to take the data. And finally, we have to take the temperature of the filament at each delta of time and each delta of distance. Eh, Here is how we calculate the conductivity with this equation and the materials that we use that are the filaments of copper, pilopropen with cocoa, a graphite with PLA, and a rice husk with PLA.
In order to calculate the thermal conductivities of each composite material, we first needed to fit the data for both temperature versus distance and temperature versus time into curves. In the first case, we used a quadratic equation to fit the curve and used this equation to find the second derivative of the temperature with respect to the time and found that for the propylene with cocoa is 4.404, for the rice husk with polylactic acid is 4.412. Uh, Then we calculated for the graphite with polylactic acid and found that it has a value of 4.420, and for the copper is 4.256. Then we fitted the data of temperature versus time into a linear equation and calculated the first derivative for each point measured, 3, 6, and 9 centimeters. The results are shown underneath each graph. Here we have the results for propylene with cocoa and rice husk with PLA. And here the results for graphite with polylactic acid and copper. Using the derivatives found with the fitted curves, we calculated the thermal conductivities and obtained three different conductivities for every filament, which means they are anisotropic because the conductivity changes in different points of the filament. The results for each filament are shown here, and their units are watt per meter per Kelvin. Discussion and analysis.
Now we are going to do a comparative analysis for the methodologies. The method that was carried out in the practice is much simple in terms of assembly to be able to take the data. In this methodology, only we need only an iron and the filaments from which we want to take the conductivity that are used. While the methodology that we propose in the group uses many more materials to be able to take the data of the conductivity of the different materials. And the methodology used in the practice use a much simple equation to calculate the conductivity since it only needs the second derivatives of the distance versus the temperatures and to solve for it in the equation.
When it comes to the behavior of the temperature of the distance, all filaments exhibit the same behavior. The temperature is lower the further away from the heat source, and it can be described by a quadratic equation. However, with the behavior of temperature over time, data follows a linear behavior, and the temperature increases over time. Also, for copper and graphite with polylactic acid, the slope or temperature change over time is higher when closer to the heat source, as shown in the graphs. Now, what affects the change of conductivity? For this, we're going to compare the thermal conductivity of pure and composite materials. The thermal conductivity of polylactic acid varies from 0.13 to 0.16, and propylene is 0.22. Here it's clear that all filaments have a lower thermal conductivity than their pure counterparts. This is because the filaments are composite materials made from non-metallic materials that add act as heat insulators. In non-metallic materials, heat is transferred via phonons or the quantification of vibrations within the crystal lattice. Composite materials disrupt the crystal lattice so that the molecules from different materials are not as linked among themselves as the pure materials, and therefore the heat transfer is inhibited. The crystal lattice also explains the anisotropic behavior of the filaments. Depending on the molecular structure of each specific section of the filament, there might be more molecules of one material or another, thus having different conductivities throughout the filament. Now we're going to solve two cases we have learned. The first is to design a structure for an ice cream parlor with an insulating layer to preserve the internal temperature, which must be around minus 4 degrees Celsius. Now, for this, we need to find a material with low thermal conductivity for the structure walls or the insulating layer so that no heat is exchanged. For this, a composite material such as propylene with cocoa would be perfect because of its low thermal conductivity, so that no heat is transferred into the inside of the container. For the second case is to design a heat exchanger where we seek to increase the temperature of a mixture of acetone and nitrogen in order to later use a flash separator to carry out the respective separation. For this, we want to increase the temperature as fast as possible, which is why we need a material with high conductivity. In this case, graphite is perfect because it's a non-metallic material with one of the highest thermal conductivities, which is why we would use graphite in the walls of the exchanger so that heat is transferred more easily and the temperature rises.
Now the conclusions. First one, the objective of the practice of determining the difference in conductivities of a poor material and a composite one was met. Also, we can determine that the four filaments are anisotropic since the conductivities at each of the distance analyzed are different. Also, we can conclude that for the poor materials have a higher conductivity than the materials that are composite. For the graphics that we made to calculate the conductivity, we can conclude that as the filament distance increase, the temperature decreases. And also that as the time increases, the temperature of the filament also increase.
Here we have the references used for this video. Thank you for your attention.